Good afternoon, everyone. My name is Alexandre Costa, and I'm here to present you a case study regarding the Monastery of Odivelas. I'd like to thank Professor Andrea Pena for the very kind invitation to be present in this quite interesting seminar, and of course also to Sadata for promoting these webinars around the world. Our case study, what I'm going to present you, is a case study in Odivelas, a city nearby Lisbon, where we did inspection and diagnosis and the seismic assessment. The presentation is divided in five different parts. First introduction, then we are going to make a small understanding about the evolution and adaptation of the monastery. Then some information regarding the structural properties, what was made, how we came out with the structural property we used in the model, and then the main part are the challenges that we face for the seismic assessment. Last, we present some final remarks. So here is the center of Odivelas, or at least the old part where we have our case study, the monastery. I have here the back of an old church, two cloisters, and I have here the main square, or at least the building you enter from this part, despite this large garden here in the back. This is the other part, so the other view. You can see here the two cloisters, here the church, and then other buildings that were attached during years. So we have in the main part, we have 11 different constructions, and then we have another one, the 12th, is an isolated building. And if you take a look to this, you have here the church, the two cloisters. We are speaking about 10,000 square meters of implementation area. And then we have 2 to 3 stories, which means that in the end, we have around 20,000 square meters of total construction area. Some start information. It is from the 13th century. Possibly the construction date is from the 1295. It took 10 years to be made, with several adaptations and damages along the years. And one of the most important was the 1755 Lisbon earthquake. That in the end, just some parts of the church and also of the cloisters remaining until nowadays from the original construction. It should be also mentioned that during the 20th century, several modifications were made, resorting mainly to reinforced concrete slabs and also some beams. Here's some historical information. You can see, for example, some mill buildings that were built around the mid of the 20th century. Here in the facade, also new openings. These two buildings. Then, for example, the gym that is building number 9 in the middle of the 20th century, with 4 main columns to support the roof, and then some supports to the balconies, where now we have reinforcing concrete slabs and the metallic roof. And the church, where we can see the original part of the church and what was damaged and what was reconstructed, and also some loss of quite interesting paintings and decorative ceilings that were lost during the years. Here we have building number 6, that is, let's say, mainly one of the most important or most interesting, with decorated tiles and walls and decorated ceilings, supported on the timber structure. And here the two cloisters, where we have stone columns supporting supposedly vaults, but these vaults, they have reinforced concrete slabs. As you can see here in cloister, it is part of number 10, and then in part 11, the same thing. Here, everything is made of reinforced concrete, and here you have a timber structure. What is going to be done in the monastery? The municipality has the objective to turn out the monastery back to the local community, because nowadays it is not used. So the main point is going to be used as a museum in some part of the church, and so this is a historical part. somehow, including this part also. Then have the municipal services in other parts, and here an auditorium, here residences for students, and here a music hall. So it's going to be a very interesting intervention, but with this occupancy, it means that we are working with building or constructions that can be considered as the importance class type 3 according to Euro Code 8. Regarding structural properties, 121 survey windows were made for timber, reinforcing concrete, and masonry characterization. Timber were defined, the properties were defined based on the species identification analysis, mainly pinus. Then reinforcing concrete, several core samples were made, as well as rebound Schmitter tests. And regarding masonry, several wall surveys were made by archaeologists because this is a national monument. It's not possible to put, or at least to define 3 main families for stone masonry, and also 2 types of brick masonry, one on solid bricks and another one with 2 horizontal holes. In addition to that, we did some flat checks. So this means that making use of all this information, the material definition was made, making use of the Italian code. Then the challenges started. The first one was regarding the seismic action. And why is that? Because being an importance class 3 building, we need to do the seismic assessment for 3 damage levels, for damage limitation, for severe damage, and for near collapse. And in our national annex, when we're working with existing constructions, we can use what is called the reduction coefficients for existing constructions. And they are here in this part. However, while for severe damage and damage limitation, they decrease the seismic action, for near collapse, the seismic action is increased. Let's look to type 1. Let's say that for severe damage, we are using just 75% of the seismic action that is considered for new buildings. But if we are doing the seismic assessment for near collapse, we are increasing the seismic demand by 62%. On the other hand, when we are working on the assessment part, so not on the retrofit, we can even reduce 90% of this action. So this means that, for example, for type 1, for severe damage, we have the seismic hazard, or at least the PGA that comes from the seismic hazard. Then you have 90%, then you have 75%, but then we multiply it by the coefficient of importance. This means that in the end, we have almost the same seismic action that is considered for new buildings with importance class of 2. So this is somehow discussable. On the other hand, if you are looking to near collapse, if you do the same calculations, we are increasing more than twice the seismic action. So this means that while here we may not be a lot conservative, here probably we are going too further and we are being too severe for the building. Regarding modeling, we have 2 approaches. The first one was what our main, or the first choice was to be made. It was individual models, so we could control better the behavior, understand better the buildings, and we could simulate different story heights. Also, can refine or do better local calibration, making use of operational model analysis results. So it could make isolated buildings. But the problem is that as they are all interconnected, the interaction with adjacent constructions is not easy to do it. And then we have another approach that was to do a global model with interaction that is already implicit in a model with the geometry, but then we have the difficulties to evaluate the individual behavior of each building, because we are looking to a global capacity curve. Moreover, using Tremuri, we couldn't, or at least to have a numerical model that was easier to control and to understand. You need to use an uniform story height, because the levels, they are more or less the same, but they have some differences, but they are not the same, but they are not so different. So this means that this could influence somehow. So one of the points was to use an uniform story height for all the buildings, but then also do a sensitivity analysis for different, 3 different story heights. We started from the individual models, but since the beginning, we decided not to go in this direction. For example, for building number 4, a simple model, this wall here is this wall. So if you do a seismic analysis in this direction, is the damage pattern, and you can see that damage concentration is here in this wall. Even the model configuration, you have just translation, so you are not connecting this building to that building. So this means that the problems probably they are not going to be this in this wall. We try also to model with some local supports, also in starting looking or modeling the remaining walls, but then we start losing the perception of the model and how the building was behave under seismic action. And the same thing came out to building number 6, that is this one. So we have here 2 perpendicular walls, and you cannot simulate this easily and control the behavior. So we start adding walls. For example, here we start adding this wall, there, here, there, but then everything started to be connected. So in the end, we decided to go to this challenge that was to build a global model. Global model, it was somehow a challenge, but it was possible to do it. It was very nice to see that Tremuri is also capable of making these large models. And then the analysis was made looking to the global models, but look individually for each building. We try also to model, or at least to adjust somehow the local properties of each building, making use of the operational model analysis results. And some example what came out is that, for example, while in this direction, Y direction, for example, this is the damage pattern for a specific point of the capacity curve, you can see that you have more or less the damage distributed along several different buildings. So you have not a damage concentrated in one of the buildings, while, for example, on the analysis on the right, you can see that, for example, in this direction, you have the damage, or at least the failures, mainly concentrated in this part, in building number 2. So this means that despite working with a global model and the global behavior, we could, or at least we're looking to the individual behavior of each building, and from there assess what was the problem and what should be tackled in the strengthening design. Then we have the problem of the out of plan. So we use also Tremuri to do it, and local mechanisms were defined based on the literature and also on the local connections that we assess on site, and also take into account the existing cracking patterns, and as well as the presence, for example, of tie rods. Moreover, we wanted also to evaluate the influence of connections between horizontal and vertical structure, so the importance of slabs and roofs, and it was also to evaluate with these simulations that it has a strong influence even for seismic demand. So this means that we need to then, on the strengthening phase, to really connect horizontal to vertical elements. So we came out with 24 local mechanisms for all the monastery. For example, here a typical gable failure, and here, for example, simple overturning or an overturning, taking into account the connection at the roof and at the floor level. This was made for different buildings, for different parts, and just to show just some 2 examples. For example, a global overturning here for building number 4, that is the building that we show in the beginning. If we connect to the top, we can increase even to 10 times seismic capacity. the same thing to other walls. So this means that on the strengthening phase of the monastery, this should be one of the key points to be used on the design. So just final remarks. So it was a real challenge of the case study, mainly to the dimension and the different wall typology, etc. And it was also important with a proper model to simulate interaction between the buildings. In order to do that, of course, you need to do some modeling simplifications, but it's very important so we can control in the end the model and understand what is going on. And we could, from the global capacity curve, take a look to local analysis. And definitely it can be said that Tremuri expedited the process of modeling and analyzing results within a reasonable time frame. Let's say that all this process took between inspection diagnosis, material characterization, ambient vibration tests, and seismic analysis took more or less 3 months. So I hope you enjoyed this presentation, and definitely if you have any question regarding presentation on this topic or any other, just send me an email by this email address. And of course, we have the contact of Ana Simões, that is a representative in Portugal, and you can also always rely on Sadata. Thank you very much for this opportunity, for this time. I hope you enjoyed, and I wish you the very, very nice webinar with these very interesting speakers. Thank you.